Hey there, and welcome. Today, we're jumping into something called geometric sequences. And I know what you're probably thinking. Oh no, a math lesson. But trust me on this one. This isn't about boring formulas. It's about a super powerful pattern that helps predict change all around us. We're talking everything from your bank account to the medicine you take. So let's get right into it with a real-world puzzle.
So let's start with a question you might actually face one day. Imagine you land a new job, and the starting salary is $26,000. Pretty good. And even better, they promise you a solid 2% raise every single year. So the big question is, how much will you be making in your 10th year? Now, you could sit there and calculate it 1 year at a time, or you could use a much smarter way.
You see, the secret to cracking this thing wide open is all about a simple, predictable pattern of growth. Once you see it, I promise, you're going to start noticing it everywhere. It's consistent, it's reliable, and it's all powered by one really simple idea.
Okay, let's get to the heart of it all. The concept that drives this whole thing is something called the common ratio. Honestly, the best way to think about it is as the growth engine for the entire sequence. It's the one number that tells you everything you need to know.
So here's the official definition. A geometric sequence is basically a list of numbers, where you get from one to the next by multiplying by the same exact number every time. Simple as that. It's a pattern that's all about multiplication, not addition. Every step you take, you're multiplying. And this slide just lays it out perfectly. Look at the left side. 1, 2, 4, 8. You see how each number is just the last one multiplied by 2? That's our guy. That's a geometric sequence. Now look at the right. 1, 2, 3, 4. You're just adding 1 each time. That's a totally different animal, an arithmetic sequence. For today, we are all about that multiplication on the left. And that constant multiplier? Well, it has a name. The common ratio. We usually just call it R. You can think of this R value as the DNA of the whole sequence. If you know R, you can predict every single number in the pattern, whether it's the next one in line or one that's 1,000 steps down the road.
So how do you actually find this magic number? It's ridiculously easy. Seriously. You just pick any number in the list and divide it by the number that came right before it. That's it. So in that sequence, 2, 4, 8, you could take 4 divided by 2, you get 2. Or you could take 8 divided by 4, and you also get 2. See? That's your common ratio. It's that consistent.
All right, so we know what a geometric sequence is, and we know how to find its growth engine. Now let's talk about the fun part. How do we actually work with it? Well, there are two main ways, and I like to call them the step-by-step method versus the time machine method.
And this slide just nails the difference. The recursive formula is your step-by-step tool. It's great for finding the very next number in line. But the explicit formula, oh, that's the shortcut. That's the time machine. It lets you jump to any term you want, whenever you want. Let's look at the step-by-step method first, the recursive formula. Now, don't let the symbols freak you out. All this equation is saying is to find any new term, which we call a sub n, you just take your common ratio, r, and multiply it by the term that came right before it, a sub n minus 1. That's all there is to it.
A staircase is the perfect way to picture this. The recursive formula lets you get from step 9 to step 10. It's easy. For our salary problem, to find year 2's pay, you just take year 1's pay and multiply it by 1.02. But, and this is a big but, if you want to know what's on step 50, you have to climb all 49 steps to get there. It works, but man, it can be slow.
And that, my friends, brings us to the time machine, the explicit formula. This thing is an absolute powerhouse. Just look at it. A sub n equals a sub 1 times r to the power of n minus 1. Let's just quickly break that down because this right here is the key to everything.
Think of this formula as a teleporter. A sub 1 is your starting point, where you begin. R is your growth engine, and n is the place you want to jump to, the 10th year, the 50th, whatever. So why n minus 1 up there? It's simply because the growth doesn't kick in until after the first term. That first term is just the starting line. You haven't multiplied it by anything yet.
Okay, theory time is over. We've got our tools. Now it's time to put them to work. We're going to use these formulas to solve that salary problem from the beginning and a couple of others, just to see them in action.
All right, let's circle back to our salary question. Now we can actually label everything properly. The initial salary, that's our starting point, our A sub 1, $26,000. The term we want is the 10th year, so n is 10. And the common ratio r, well, a 2% increase means you keep 100% of your salary and add 2%. So you multiply by 1.02 each year. That's our r.
And now for the magic. Instead of grinding out the math for year 2, then year 3, then year 4, we just plug those numbers into our time machine formula. That's 26,000 times 1.02 to the power of 9. And boom, in our 10th year, the salary would be about $31,085. So much faster, right?
But here's what's really cool. This pattern isn't just for things that grow. It also works perfectly for things that shrink or decay. Let's look at a new situation. A patient takes a 30-milligram antibiotic. Every hour, 10% of that medicine is processed by their body and is no longer active. So the amount is going down over time.
So let's break this one down. Our starting point, A sub 1, is 30 milligrams. Now here's the key. If 10% of the medicine leaves each hour, that means 90% remains. So our common ratio, our R, is 0.9. And notice that number is less than 1. That's the secret code for decay.
And just like we did with the salary, we can use that exact same time machine formula to jump ahead and see what's happening later. We can instantly figure out how much medicine is left at hour 7, hour 12, or even a full day later, without doing all the steps in between. It doesn't matter if it's growth or decay, the math underneath is the same.
Let's do one last quick one, just to make sure this is totally locked in. A small school has 284 students, and the student body grows by 4% every year. The question, what's the population going to be in 7 years? You can already see the pattern, right? A starting number, a percentage growth, and a period of time.
So if we plug that into our formula, a starting value of 284, a common ratio of 1.04, and we're looking for that 7th term, we get an answer of about 374 students. See? Once you have the right tool, these kinds of changes become incredibly predictable.
All right, we have covered a lot of ground here, from making money to fighting infections. So let's boil it all down. What are the absolute key ideas you need to walk away with today?
Here's the bottom line. First, geometric sequences are all driven by that constant multiplier, the common ratio. Second, if that ratio is bigger than 1, things are growing. If it's less than 1, things are shrinking. Third, that explicit formula is your time machine. It lets you jump to any point you want. And finally, and most importantly, this is not just abstract math. It's a real pattern that helps us predict real things in the world. So, I'm going to leave you with this question. Now that you know the signature of a geometric sequence, that constant percentage change, where else do you see it? Think about compound interest in a savings account, or how the views on a viral video explode, or even how a rumor can spread through a community. This pattern is absolutely everywhere, and now you have the tools to see it. Thanks so much for joining me.